All right, so now we're going to implement that behavior that you just saw in the visualization. We're going to add the memory, the single value memory. So we're adding support for a mem and a recall operation, where mem is going to capture the value in the memory and recall is going to bring it back to the the main value in the calculator, which for us is the out signal. So the first thing we need to do is actually add those two operations. So far we've got a calculator that can do up to 4 operations. So we've got an op signal that currently is 1 to 0 to encode those 4 possibilities. And now we're adding 2 more possibilities, so we need to add a bit here. So we'll extend op to 3 bits. Next, in step 2 is to actually add the memory itself. So as with most state, the memory is you'll see this sort of pattern where you have a mux that's deciding how to update that state, and that mux will then cross a stage boundary, which implies the flip-flop that's holding on to that state from one cycle to the next. And then that value, if we're not changing it, gets recirculated back around. In this case, we're recirculating it back with a 2-cycle loop. We could actually do this with a 1-cycle loop as well. I'm just keeping this design all consistent with the 2-cycle, 2-cycle cadence. So in this case, a value that we see in the memory on one particular cycle, if we're holding on to that value, we're going to see that value 2 cycles later after it's recirculated through this path. Just a little bit more about the recirculating mux on state. So, assuming we had done this with a 1-cycle loop, generally in Verilog when you're coding, and this course isn't about Verilog, but just because many people I'm sure have seen Verilog before and are used to it. Generally in Verilog you tend to provide code that's going to update the state only when there is an update to the state. In TL Verilog, I think it's a bit cleaner to be explicit about the values for all cases. So we're generally explicit about the recirculation path, which implies this recirculation into a mux. Logic synthesis tools can actually optimize away the mux depending on the physical trade-offs. Holding on to state doesn't have to recirculate through a mux. You can often control the flip-flop to control the clock input to the flip-flop and avoid avoiding the clock, similar to what we talked about with clock gating. This is a form of clock gating called functional clock gating because it impacts the behavior of the model. You can use that clock gating to avoid updating the value in the flop. But anyway, that's all sort of beyond the introductory level here. We're going to be explicit about all these recirculations through flip-flops. Here we have this 2-cycle loop where a value in 1 cycle is going to appear 2 cycles later, and we don't care what happens in that cycle in between. That's actually going to be where we're conditioned off. We're going to see grays in the waveform. Okay, so all right, back to this actual memory, right? So what are the update cases? It's state, just like the output. We're going to provide a 0 input. I don't know why I didn't put a 32 tick B on there, but either way is fine. So we have our 0 input for reset, and we have our retain case, which we've been talking about around this path. And then we have the case where we're doing a memory operation. So if we're doing a memory operation, and as I've drawn it here, we're encoding that memory operation as a value of 5 on the op input. If we're doing a memory operation, then we want to grab the value of output and capture it in the memory. Sorry, that wasn't the path. We're grabbing the value of output from 2 cycles ago and capturing that in the memory. All right. And we could actually hook that up through 1 cycle, or through even immediately from the output of this mux. because in this case, where we're doing a memory operation, the value on the output has been stable for 2 cycles. But it's sort of more regular to say we're taking the value that was computed 2 cycles ago from the previous operation and using that as the input to our memory. Alright, so that's all the hookup, and you can implement that. And after implementing memory, the memory operation, we can implement the recall operation, which is kind of doing the opposite, taking the value out of the memory and feeding it back into the output value selected by recall. So that looks similar, and after you've implemented it, of course, verify your behavior in simulation. If you'd like, you can use the shell that we're providing that I talked about for implementing this lab, and you can see the visualization also showing you what's happening in simulation. And when you're done that, come back and we'll move on.